Hello, in this video we are talking more about reaction rates. You should have just learned in the last how to determine the order with respect to a single reactant and the overall reaction rate. But let's talk about more of what those actually mean. Whenever we have a zero order reaction rate, that means that the rate of the reaction is the same regardless of the concentration of that reactant. So if it's zero order, our concentration is raised to the zero power, and anything raised to the zero power is 1. So for our rate law, our rate is simply equal to K. Doubling A or changing the concentration of your reactant in any way will have absolutely no effect on the reaction rate. Because of that, the rate is also independent of time. As time goes on in a chemical reaction, your reactant concentrations decrease. Well, that decrease in rate over time and concentration over time is not going to affect the rate since it is zero order, and changing the concentration has no effect on the rate. Whenever we have a first order reaction, our rate is directly proportional to the reactant concentration. So our concentration is raised to the first power, so doubling the concentration of A would double the rate of the reaction. If we half the concentration, it's going to half the rate. If we multiply the concentration by 6, the rate is going to go up by 6, so directly proportional. When we have second order, our rate is directly proportional to the square of the reactant concentration. So our reactant concentration is squared, and that is directly proportional to our rate. So doubling A would quadruple the reaction. So we'll always have the square of the effect that you had on the concentration. We also need to be able to experimentally determine our rates, but let's look at this graph here first. We can see that we have our rate versus concentration. When it's zero order, we are changing the concentration as we move along this x-axis, but absolutely nothing is happening to the rate. That's what zero order means. Whenever it is first order, it's going to be directly proportional. So as we go from point 1 to point 2, our rate is going to be doubled from 0.002 to 0.004. Whenever we have second order, doubling the concentration is going to quadruple the rate. So we can see that as we double our concentration from 0.2 to 0.4, we have that quadrupled concentration there. So that is what those orders actually mean. Again, we can determine these orders experimentally. Whenever we have a reaction with multiple reactants, we have to change the concentrations of one single reactant at a time and see how that's affecting our overall rate of reactant. While we're changing the concentration of that one single reactant, we have to hold all other reactants constant, so we can see the effect of just the one single reactant on the rate. If we're changing multiple reactants, we don't know which one is causing any change that we see in the rate. And so then we would go and conduct multiple trials, changing the concentration of each reactant one by one and measuring the change in rate of each change to figure out the order of each. So a lot of times you're actually going to be given the experimental data and asked to determine the overall rate law or the order with respect to each reactant. So let's look at our first example of this. So we have our reaction that's happening here. So here we have our two reactants. We're changing those two different reactant rates over several different two different reactant concentrations over several different experiments to determine the change in rate. So again, we're going to hold one constant while changing the other. As we compare trial 1 and trial 2, we can see that the concentration of NO was doubled. The concentration of Cl2 remained constant, so just like we need to do, hold one reactant constant while changing the other and see what effect doubling the NO had on our rate. Rate went up by 4. We went from 1.2 to 4.8 with that same 10 to the power of -6. So from this, we're able to determine the order of our reactant. When we double our concentration and the rate quadruples, that's second order. The other way that we can look at that is 2 squared is equal to 4. So that since 2 squared is equal to 4, that tells us that our reaction rate with respect to that NO is second order. Whatever that power that is needed to reach the change in the rate is going to be your overall order. So 2 to the x power is equal to 4. Well, we solved for that x and it is 2. That means we are second order. Whenever we see problems like this, we're generally going to have to justify our answer. So basically we need to go put out in words the steps that we just went through. As we look from trial 1 to 2, we saw that the concentration of NO was doubled while the concentration of Cl2 was held constant. This caused the reaction rate to increase 4 times. Therefore, the reaction is second order with respect to NO. So we would again want to just put that all into some justification. So as we write that concentration, again, we would want to look at which trials we are going to and from. So trial 1 and 2, what's happening to the concentration of each reactant? NO is doubled, Cl2 is constant. What's happening to the rate? It went up by 4 or it's quadrupled. That information tells us that the reaction rate is second order with respect to NO. Be careful here and make sure you do say that it's just respect to NO. It's not with respect to the concentration of NO, just NO, the reactant. So let's also try and determine our rate for our Cl2. So as we compare trials 1 and 3, we can see that now the concentration of NO is remaining constant and we're changing Cl2. So to experimentally determine these rates, we always have to hold one constant while changing the other. So again, between trial 1 and 3, the NO is now held constant while changing Cl2 so that we can determine the order with respect to Cl2. Our Cl2 concentration is doubled, and we can see that our rate doubled as well from 1.2 to 2.4. So when determining that rate, we look at 2 to what power equals that 2 times change in rate? Well, 2 to the first power equals 2. That means that our reaction rate is first order with respect to Cl2. Whenever we doubled the concentration, the rate doubled. That is what first order mean. Again, we need to justify our answer. So we need to talk about what trials we're going to and from, what happened to the concentration of each of our reactants, how that affected the rate, and what we learned from that. So again, from trial 1 to 3, we saw that Cl2 was doubled while the concentration of NO is constant, causing the reaction rate to double. Thus, the reaction is first order with respect to Cl2. Make sure we're just saying Cl2 and not with respect to the concentration of Cl2. So just Cl2, the reactant. So when we're given this experimental data, we can determine the rate law now because we know our order. Rate is always equal to our rate constant times the concentration of each reactant raised to its order. So our NO was second order, so raised to the second power, and our Cl was first order, so raised to the first order. We can also solve for the rate constant. We are given all the other pieces of information that we need. We have rates and we have the concentration of each reactant. We just need to pick one single trial to use. I'm going to use trial 1 to calculate my rate constant. To do that, again, we just need to plug in all of our information from trial 1 into our rate law. We have our 1.2 times 10 to the negative 6 rate equal to k times our 0.2 squared times another 0.2. So I can rearrange so that we are solving for k and added my units as well. Units of rate are molarity per second. So we have our rate up top in molarity per second. We have 0.2 to the third now, and those are concentration, so those are all molarity. So when we do this math, we get our value of k as 1.50 times 10 to the negative 4, keeping our 3 sig figs, but we still also have to solve for our units of k. Solve for our units of k, we can kind of just do the math with that as well. We have molarities per second divided by molarity cubed. We need to see what that is going to give us. So when we have that, when we're dividing by our molarity cubed, that's the same thing as multiplying by 1 over our molarity cubed. So one of our molarities is going to cancel, so that top molarity will cancel with one of these guys, and so we get 1 over molarity squared seconds as our units. We could also express these units as the inverse, so molarity to the negative 2 power and seconds to the negative 1 power. So unit-wise, one of those two guys there. Again, we can just do dimensional analysis, or basically the math with those units, and see what cancels out and what is left to find those units of k. So lastly, in part E, we're looking at trial 3. We want to calculate the concentration of Cl2 remaining when 25% of the original amount of NO has been consumed. Well, it's giving us information about NO and asking about Cl2. This is a stoichiometry problem. We have to figure out when 25% of the original amount of NO has been consumed, how much NO is that? That's how much NO reacted. Well, if we know how much NO reacted, we can figure out how much Cl2 reacted. And then we know how much Cl2 we started with. We can determine how much Cl2 remained. So 25% of our original 0.2 molar NO is 0.050 molar NO. I went ahead and split that up into moles over liters, since that's what molarity is, so I can use my mole ratio from NO to Cl2 to see how many moles of Cl2 reacted. So our ratio from our balanced chemical equation is 2 moles NO to our 1 mole of Cl2. So this is going to cause our moles of NO to cancel out. We're left with moles of CO2 over liters, or the molarity of Cl2. So this is the molarity of Cl2 that was used or reacted. We want to know how much remained, so we need to subtract that from our original amount. We originally had 0.4 molar in our trial 3. We just determined that we use 0.025, and so that means we have 0.375 molar Cl2 remaining. Lastly, we can do this exact same thing whenever we have gaseous reactants. If we have gaseous reactants, we're going to be given partial pressures rather than concentrations. But that pressure is directly proportional to concentration. It is the exact same process. So take a minute, see if you can determine the rate law for that reaction. That means that we need to use our experimental data to determine the independent order of each reactant before we write that rate law. Then we need to justify our answer. So which trials were you looking at? What happened to the pressure of each reactant? And how did that affect the rate and determine the order? So give that a go. Resume the video when you're ready to check your answer. As we look from trial 1 to 2, we can see that our pressure of NO is constant. while the pressure of H2 is doubled. So we had to find some place that NO was staying constant, so where one stays constant and the other is changing. So we could have also looked at trials 2 to 3, but that's just a little bit harder math there, where from trials 1 to 2, we just have that straight up doubling that caused our rate to double. So 2 to the first power is equal to 2, therefore H2 is first order. We would want to go and include this in our justification, so we can go ahead and justify that part. So again, pH2 is doubled while pressure of NO is constant. The rate was doubled, thus the reaction is first order with respect to H2. We also needed to find our respect with NO. So I need to find some place where H2 is held constant, and I'm looking for that easy math. From trials 4 to 5, pressure of NO is constant while H2 is doubled. That's going to cause our rate to just about quadruple. So 2 squared is 4, so that means we are second order with respect to NO. We need to go and justify this as well. So since our pressure of NO is doubled while pressure of H2 is constant, quadrupled the rate, the reaction is second order with respect to NO. Again, we want to make sure we're just saying with respect to H2 and NO, not like the pressure of H2 or the pressure of NO. Now we're ready to write our rate law. We write that rate law is always our rate constant times the concentration, or we could use the pressure here. Pressure of NO, or the concentration of NO, should be squared, and your pressure or concentration of H2 should just be raised to the power of 1. We're going to be practicing more in class about determining these rate laws from experimental data, but until then,